All right, everyone, we're gonna go get started. If people join late, please send them that sign-in link. We are recording this, so if you have to leave early, then that's totally fine. You can see the recording on our YouTube, and then I'll be posting these slides and the recording once it's done being edited. I'll be posting that in the Discord, so just keep an eye out for that. So today we're going to be talking about Game Boy reverse engineering. So I'm going to be going over kind of the architecture of the original Game Boy, kind of describing how it works, and then we're going to get hands-on experience reverse engineering a Game Boy ROM. So it should be fun. Feel free to stop me at any time with questions. You can either write it in the chat or you can turn on your mic and just say your question. But yeah, feel free to stop me at any time because Game Boy can be kind of weird with how it implements certain things. So I definitely understand if it's not intuitive and you need more clarification. So just as a background, Game Boy refers to a line of different handheld electronic devices, gaming systems created by Nintendo. So most of you are probably familiar with Game Boys, and many of you may have had one growing up or even have one now. So there's been a line of different Game Boys, different models. Today we're going to be talking about the original Game Boy from 1989, and that's in the top left corner. So that's the one that doesn't have color. It doesn't have advanced backlighting. It's the simplest architecture, and it's I would say the easiest to reverse engineer. So it's a really good starting point for getting to know Game Boys. The others are pretty similar, but there are some major differences because, like with the Game Boy Advance, they actually use a whole different CPU. They use an ARM-based CPU, and we'll talk more about the differences. But yeah, today we are going to be focusing on that 1989 original Game Boy. So as an overview of what composes that Game Boy, what its architecture looks like, it has an 8-bit CPU. It's a custom one, so that Sharp LR35902. It's pretty much a hybrid of the Intel 8080 and the Zilog Z80, but it has a couple quirks that make it different. It has an 8-bit data bus and a 16-bit memory bus. So you'll see most of the instructions are 8-bit, but they could be referencing 16-bit addresses. So that's an important clarification because it'll help you kind of understand when you're interacting with the assembly code in reverse engineering. There is a 8 kilobyte internal RAM, but it can be extended to 32K. The video RAM is separate from that, and it's 8 kilobytes internal. And then ROM, there can be different size of cartridges, all the way up to 4 megabytes. So those are the biggest cartridges. You don't see them very often. You normally see 32K. That's the kind of like go-to size for ROMs on cartridges. So either 16 or 32K, but they support larger ones, and depending on what game, they may need more space. It may be a more complex game and have more instructions or have more graphical data. So it can go up to that 4 megabyte cartridge size. The sound, there's 4 different channels of sound, and you can redirect those to the left or the right speakers. And it does a lot. There's like a lot of like additive effects. So you can add the sound from one channel to the sound of another channel to kind of layer it. The sound is probably the most complicated, so I'm not going to be talking about it too much today. And it also doesn't play a huge role in reverse engineering. At least I've never seen a challenge that actually took advantage of the sound capabilities of Game Boy and used that as the crux of their challenge. Like, I haven't seen anything where you have to basically reverse engineer sound bites or anything like that using like SDR or something. Most of it is pretty much you have to like crack a code, or you have to get your sprite into a specific position. So we'll talk more about CTF challenges, but I just wanted to say that to kind of justify why I'm not spending as much time describing the sound as I am describing other parts of the Game Boy. For graphics, it has a 160 by 144 pixel display, and it only supports 4 shades of gray, so you can't get too crazy with that, but you can definitely show a decent amount of detail with 4 colors. And then sprites, it only supports 40 sprites at a time, so those sprites can be either 8x8 or 8x16. It has a serial port. That serial port is used for connecting external peripherals. So if you played like some of the Pokemon games, you could use a transfer cable to connect 2 Game Boys together, and you could transfer your Pokemon from one Game Boy to another through a serial port. So there's a bunch of different external peripherals that have been made for the Game Boy. I'm not going to go into too much detail with those. If you want to know more about those external peripherals, I can hook you up with resources that describe like how they work. A lot of them have actually been reverse engineered because the documentation, like the original documentation, is not available for them. Cartridges, they can be various sizes. They're 32 pin. The Game Boy does have a DMA controller, so that's useful for basically addressing additional memory outside of like RAM, ROM. So like if you need to expand the memory that's available to you, you can use a DMA controller. Then there's also support for interrupts, and interrupts are pretty essential to the functioning of the Game Boy and the ability to play games. So if you wanted to kind of understand what the underlying hardware looked like, you can kind of see kind of the pinout here. So I don't expect this to really mean anything to many people. But if you are really excited about hardware, you can dive into this more. Basically, it just maps the pins from like the CPU to the SRAM and shows like the game cartridge 32 pins. So you can see on the far right, there's that game cartridge socket that shows those 32 pins and what they connect to. Yeah, it's more just for your own interest. It won't help us with actual reverse engineering in terms of reverse engineering the ROMs. We're not going to be reverse engineering the hardware of the Game Boy. We're just going to be focused on the software, the ROM. So like I said before, the Game Boy, the original Game Boy uses an 8-bit CPU, and it has kind of a hybrid approach between the Intel 8080 and the Zilog Z80. So most of the commands or instructions are 8-bit, but there's also like 16-bit loads and 16-bit arithmetic operations. The CPU runs at 4 megahertz, so that is much, much slower than your computer's CPU. So when you're running an emulator and you're trying to play a Game Boy game, they have to actually scale. They have to like accommodate that 4 megahertz rate. So they're actually slowing down how fast your CPU processes the emulated instructions. So that's something to keep in mind if you're doing any emulator development. You have to basically get the timing right, and you have to write your emulator to expect that 4 megahertz rate. Some of the different types of instructions that are supported are those 8 and 16-bit loads, 8 and 16-bit arithmetic operations. So that's your like add and subtract. Your logical operations, so like OR and XOR. You've got some bitwise operations, so you're basically flipping bits in an address or in a register. You can also issue commands to the CPU to tell it to stop or to halt, to reset, to enable instructions or disable instructions. There's rotate and shift operations, conditional and unconditional jumps. So they use JP for their jump instruction, but they also use it for their unconditional jumps. Basically, they'll have like a compare instruction, and then that will set a flag, a condition flag in the F register, and then you use JP and then whatever condition flag that you're looking to compare. So if you're comparing two numbers and seeing if they're equal, then that would affect the Z flag. So you would do JPZ, and that would basically tell your CPU that, hey, I'm interested in jumping only when that 0 flag is set. Then there's calls and then returns. So that's for calling different functions. And then there's other miscellaneous instructions. In the instruction set architecture for a Game Boy, it utilizes 8 general purpose registers, and those are all 8-bit registers. So those are A, B, C, D, E, H, L, and F. So you can combine those registers to form 16-bit register pairs. So you can combine A and F to make AF. You can combine B and C to make BC. You can combine D and E to make DE, and H and L to make HL. But one really important thing to note is that the F register is a read-only register. It's used for holding those flag bits. So we discussed on the previous slide how when you're comparing two numbers that like if they were to be equal or not equal, that would affect the Z flag. That Z flag is 1 bit in this F register. So basically, you as a programmer cannot issue instructions to write to that register. So basically, when you're doing operations, you really only want to use A, B, C, D, E, H, and L. There are 2 special purpose 8-bit registers. So there's the PC, the program counter. So that's basically to keep track of where you are in the ROM, like when you're executing instructions. So it just points to the current instruction, and it helps the CPU basically keep its place in the program. And then there's the stack pointer, which points to the top of the stack. Then one thing to note is that the argument order for these instructions is the destination comes first and then the source. So you can see it in the examples we have below when we're describing the different types of loading. So there's multiple types of loading that is supported. So there's immediate loading, indirect loading, stack loading, and loading register contents to memory. So when I say immediate loading of registers, I mean you're loading some exact value into a register. So you could be loading the number 3 into that register pair DE. So that register pair DE will be equal to hex 3. Well, it'll be storing hex 3. In this example, I'm storing the hex value FF80, which represents a memory address, but I'm just storing FF80 directly into DE. I'm not accessing any memory at that location. I'm just storing FF80 into the register pair DE for immediate loading. For indirect loading, you are accessing whatever is in like HL. So you're just loading that into D. For the stack, that describes basically restoring the value of a register, or basically just popping the top value off of the stack and then storing it into a register. So in this example, it's popping the top value off the stack and storing it into register pair BC. Excuse me, I'm just going to take a quick drink. And then the last one is loading to memory. So basically you're loading whatever is in the content of that source register, and you're going to be loading it to an address in memory. So you're loading the contents in A and storing it at C000. So did that make sense? Does anyone have any questions before I keep going? Okay, I see. Okay. All right, then we'll keep chugging along if there are no questions at this time. So one of the most important things to know when you're working with a Game Boy is knowing where everything is mapped in memory. So this is a fantastic diagram that kind of lays out your different sections of memory and what they correspond to. So from 0000 to 7FFFF, that is going to correspond to the space that you use for your ROM. So basically, if you have a 16 kilobyte ROM, that's going to get stored in 0000 to 3FFFF. If you have a 32K one, it's going to get stored from 0000 to 7FFFF. So that corresponds to that fixed home and home region. And one thing to note is that when you load your cartridge, there is some like set amount of data. There's a certain number of ROM instructions that always have to be present to basically get the Game Boy into a state where it's ready to play the game or load any further data. So it's basically setup information. And that's also where like that Nintendo logo pops up, is in that kind of like initial setup period. So that has to be present in every cartridge. So it has setup and it has copyright stuff. So that's just useful to know. Then you also have your different RAM sections. So you've got like your VRAM or your display RAM as it's described here. Expanded work RAM, I believe that's also corresponds to OAM, but I could be wrong on that, so don't hold me to that. And then there's the internal work RAM. So these RAM sections are used for different parts of like mainly for graphics. So the RAM sections are mainly used for graphics, but it also holds other data as needed. So this is another diagram that is useful to get an idea of how memory is laid out. So you've got your cartridge header area, which I described. That's at hex 100 to hex 14F. Restart and interrupt vectors, those are basically defined in the area from 0000 to 00FF. And then that's part of the ROM, and that ROM section can go from 0000 to 7FFFF. Then character RAM, which is like sprite information, that's going to be 8000 to 97FF. Then background data for graphics, so your background, all of that is so you can have two backgrounds defined at the same time, but you can only have one loaded. So background 1 is at 9800 to 9BFF. Map 2 is 9C00 to 9FFFF. Then if the cartridge needs additional RAM space, then you have it in that next section. Then there's internal RAM, which is basically set aside RAM that is mapped from the cartridge. Or sorry, I may be misspeaking there. But you can have up to 8 banks. Bank 0 is always going to be there from C000 to CFFF. Then bank 1 through 7, they can be switched in and out, and they're in that next section. OAM, object attribute memory, is used for sprite data. So that's at FE00 to FE9F. For hardware I/O, so that's your user input. So like if you're sending button presses to control your character, those registers are in FF00 to FF7F. So those registers will hold the state of those buttons. Then there's interrupt flags and other miscellaneous. So that kind of gives you an overview of how this memory is laid out. Then kind of a background on how the graphics work. So like I said before, it has 160 by 144 pixel graphical output. It uses ARGB values for those pixels, but it only supports white, light gray, dark gray, and black. So you're not really getting a lot of color out of it. It's just showing you a couple different shades. In later Game Boys, like the Game Boy Advance, Game Boy Color, they add more colors. So unfortunately, with Game Boy Original, you didn't have a lot of variety. And then this data is stored in both VRAM and OAM. And then several registers can control what inevitably gets rendered. So if you, we'll go further in the next slide, but like LCDs, scroll Y, scroll X, scan line, current palette, when pause X, when pause Y, all of those are used to control what gets rendered. And then the LCD register is the main control register for graphics. So it's used to kind of like enable or disable display, enable windows or enable sprites, and so on and so forth. And it has its own I think 2 interrupts associated with the LCD register. So whenever anything is rendered, chances are there's going to be some sort of corresponding change to the LCD register. So the background is composed of 32 by 32 matrix of tiles, and each tile is 8 by 8. So that corresponds to a total resolution of 256 by 256. But if you remember, on the previous slide, we said the Game Boy only has 160 by 144 graphical output. So how does that work? How can we have a background that's bigger than the graphical display? And the way that works is through scrolling. So if you've ever had a Game Boy, you remember moving your character to the edge of the screen, and then the background scrolls with your character. And that's because that background is bigger than the graphical display. So you can have a background of up to 256 by 256, and that would be a scrolling background. You could also have an exact background where it's 160 by 144. But it's up to the individual developer how they want to make their background scenes. And then each background, there's 2 background tile maps that you can have available to you, but only one can be displayed at a certain time, and those are stored in VRAM. There's also a concept of windows. So it's similar to a background, but it kind of just overlays. So it's not scrollable. It's not going to be 256 by 256. Max is 160 by 144 for that window. And it's positioned with win pause X, win pause Y. And the reason why there is this concept of windows is to kind of achieve a layering. So this is kind of the extent of layering you can get with the original Game Boy. Then there's sprites. So these are probably what you're most familiar with. A sprite is basically a character. It's some smaller tile that you can control or you can interact with. It usually has some sort of script connected to it. These are overlaid on top of the background. And then depending on the window, they can be either overlaid on top of the window or underneath the window. They can have different colors. So each sprite or tile has its own color palette, and you can actually trigger between the different color palettes. Once again, we're not getting too wild with the 4 colors that are all variations of white and black. So that color palette isn't crazy, isn't too exciting, but it does have the ability to have different color palettes. And then the position, priority, like above or below that window, or above another sprite if they overlap. Orientation and size, all of that information is stored in registers in OAM. So OAM holds the sprite table memory. All right, before we start talking about user input, does anyone have any questions on graphics? All right. Okay, yeah. It is different how they have dedicated space for each thing. So like they have dedicated sprite memory and then dedicated background memory versus using the same memory space and then just kind of clearing it out and writing to it when needed. And the reason why they have those dedicated memory sections specific to graphics is because there's many things happening at once. And if they were to all use the same address space, it's almost guaranteed that things would overwrite each other. So having the dedicated spaces for each aspect of memory, at least for the Game Boy architecture, was a necessity because they needed to be able to manipulate sprite memory at the same time as background memory. And they didn't want things overwriting each other. Does graphics compression play into these Game Boy CTF challenges? What do you mean by graphics compression? Like, are you talking about the scrolling? Everything is defined in terms of pixels, so you can only represent, like you can only have graphics that are represented with pixels. So I don't know. There's no compression. Basically, when sprites are stored or when backgrounds are stored, it's stored as is. There's no compression of those sprites or those backgrounds. I don't even know if it would be possible to have a like larger image and then compress it down and have it stored in memory based on the constraints of like the Game Boy architecture. Okay. There's video way back on compression on some handheld. I may be like not answering your question properly or not understanding fully what you mean by that graphics compression. So I could be going down the wrong track here. Like if you do want to represent a normal PNG, like a normal image, on a handheld console, you would have to use an external tool to convert it to a tile map, and then have it represented in terms of pixels in the size that the Game Boy requires. It will absolutely crash if you have it in sizes that it doesn't expect. If you're talking about emulators and having compression in terms of scaling the windows to that display, to that 160 by 144 display, then there definitely could be some compression at play there. I think I would need more clarification to answer your question properly. I'm sorry about that, Ben. So I'm gonna go on to user input, but if you have any more questions on graphics, feel free to shoot them in the chat and I'll try my best to answer. Unfortunately, I don't know everything about the Game Boy architecture. I wish I did, but the documents are very long. You can read hundreds of pages of documents and still not know everything about the Game Boy architecture. There's a lot of things that are undocumented. So I'm kind of just giving my best like impression and best understanding of the architecture. And I tried to condense it so it wasn't just me throwing a ton of information at you that wouldn't be useful to reverse engineering a ROM. So now just talking about user input. So user input is handled with the Joy P register. So that's for joystick. That's why it's called Joy P. It holds values for start, select, A, B, and then that directional pad. So up, down, left, right. And then each time that one of those buttons is pressed, an interrupt int 60 is raised, and that's used to signal a change in the state of these buttons. So that's basically how it works. The values of start, select, A, B, and the directional, like the directions, those buttons, their state is represented with bits, just ones and zeros in that Joy P register. So it makes it pretty easy to tell if a button is being pressed, and then the CPU can respond accordingly based on subsequent instructions. So for reverse engineering, some of the tools that are really useful are Ghidra, and then there's an extension called GameBoy. That's kind of the state of the art in terms of Ghidra, is using it with GameBoy. GameBoy is a Game Boy processor module that was written by, I'm blanking on the username of the person who wrote it, but it's written by one person, and it does a pretty good job of understanding the Game Boy instructions, the assembly instructions, and then providing a C decompilation. So I will be showing you what Ghidra and GameBoy look like once we get going with the exercise. You can also use Radar2 or Radare, however you pronounce it. R2 is pretty good when it comes to Game Boy. I've used it before for reverse engineering a ROM, and it handled it pretty well. IDA Pro you can use, but you would need the Pro version if you wanted to do anything with the Game Boy architecture. So unless you have a license from your company, chances are you're not going to have access to IDA Pro and not going to be able to use that tool. So I would highly recommend Ghidra or R2. Binary Ninja, I'm not sure what their support is. I meant to look that up beforehand, and I forgot to do that. So I apologize for that. I would assume Binary Ninja would handle Game Boy just fine. I haven't used it for any Game Boy reverse engineering, so I can't speak to the stability or how well it interprets the assembly. So I will need to update the slides and reflect its current capabilities for that. There's another tool called MGB-DIS, which is used to basically take a ROM and then disassemble it to all of its assembly instructions, and then it just outputs it to a text file. So that's useful if you want to look at specific sections of the ROM. It's not going to be as useful as like Ghidra or R2, because you're not going to be able to have an interactive disassembler, like a disassembly window, and you're not going to have a decompiler there. So it's useful if you already know kind of what area that you're looking at for the ROM, and you just want another interpretation, basically, if you want to double check yourself, or if you're in a resource constrained environment and you can't run Ghidra because of memory issues or something like that. Then for debuggers or emulators, these are kind of the top 4. There are additional ones, but I haven't used them, so I don't feel comfortable recommending them one way or another. I will be showing you MGBA, BGB, and Visual Boy Advanced today, but I will be doing most of my work with BGB. So I recommend, if you're planning on following along with the exercise, that you use BGB, because it'll look the most similar to what I'm doing, because I will be using BGB. And I think also it's the most straightforward of the 4. I like its interface the best. It's pretty stable, and you don't need to configure very much. You can just load a ROM, and it's really good at auto-recognizing what settings it needs. So just a note, patching in Ghidra can be tricky. It can be weird. And that's true of multiple architectures, but especially Game Boy. So a lot of the times patching Game Boy ROMs and Ghidra will fail, and that's almost certainly due to the order of the ROM sections in the binary. So when Ghidra goes to disassemble the binary, it will sometimes scramble those ROM sections, and then when you're trying to patch, it will be patching the wrong part of memory, and it won't work. So someone actually developed a Ghidra script that you can use to fix the order of the ROM sections before you patch. So I included that script below. And then I compiled a list of different Game Boy challenges that I've seen and are pretty good at getting you familiar with the Game Boy architecture. There are some other ones I didn't include, and that's because I didn't think they were closely related enough to Game Boy architecture, specifically DEF CON's Game Boy challenge. So that one was a PON or binary exploitation challenge. And it basically was like a Game Boy emulator, but the underlying exploit did not have to do with the Game Boy architecture. So it was more to do with the server. So that one I didn't include because you didn't have to patch a ROM, you didn't have to find a vulnerability in a Game Boy emulator. You had to find a vulnerability in a Game Boy emulation server, but it wasn't exactly related to the Game Boy architecture itself. So I included some other ones that I think are a little bit more related to Game Boy. Also, just a note, if you're trying to find at gunpoint the Hacklu 2014 challenge, do not look for write-ups through CTF time for that specific challenge. The reason why I'm saying that is because there is a Russian team that has a write-up for it, and their website either was compromised or is malicious, or they have a malicious ad network that they utilize, and it serves malicious ads. So you get redirected to another site that auto downloads some malicious files. So I highly recommend being very careful with the Hacklu 2014 challenge. If you need that challenge, let me know. I will do the hunting for you. I will put my computer on the line. Because, yeah, I was trying to gather up challenges last night, and the Russian CTF team's website redirected to that malicious site and downloaded files. And thankfully, because I didn't have anything set to auto run, I was okay. But I spent like 3 hours looking for indicators of compromise, running scans, going through my event logs. So I don't recommend you go through that experience. Also, backups. Always have backups of all of your important files in case you do get compromised, so you can restore it easily. Today we're going to be going over Square CTF's 2017 challenge, which is called the Turing Agent. So that's going to be the one we're going to use if you want to follow along. And then good write-ups for those challenges. I've included those below. That Hacklu 2014 Gunpoint write-up is not the one that sent me to a malicious link. So that one's okay. The link I included here is okay. Do not go to the write-up that is linked on CTF time, because that one is the Russian one that will serve you malicious ads. So just as a heads up. And I'll put a disclaimer when I upload the slides as well, because I don't want anyone having issues or getting compromised. And then this is kind of on the other end. This isn't on reverse engineering. This is on development. These are two tools you can use if you want to develop your own Game Boy ROMs, and then either use them through an emulator, or you can actually buy cartridges that you can flash. So you can use Game Boy Studio, which is what I would recommend. It has the easiest development process. It's pretty much like Scratch, if you are familiar with MIT's Scratch. It's kind of drag and drop block programming, and then you add in some scripting, some triggers, stuff like that. Pretty user friendly. It's very stable. I haven't run into too many issues with it. Then there's also RGBDS, which I have seen recommended all over the place, but I haven't personally used. So that's, I would say, use RGBDS if you have a lot of experience with Game Boy and you understand the assembly pretty well and you can hand assemble it. And then I also included resources for different aspects of Game Boy. So architecture, hardware, development. I'll be adding some other links to this, but this is a good starting point. Pandocs, which is that second link on there, that is your bread and butter when it comes to Game Boy. It's the standard for the documentation. Like, that is where most of the information lies. It's either in Pandocs or it's in the Game Boy programming manual, which I included below as well. So now the moment that everyone's been waiting for, I bet. We're going to be reverse engineering a Game Boy ROM. So I will be sharing that over Discord and in the chat. So give me a moment and I will upload that ROM. And then I will walk you through how to use Ghidra and Ghidra Boy and then BGB to solve this challenge. And then that should give you a pretty good starting point for solving additional challenges, especially those other CTF challenges that I included in the slides. All right, give me a moment. I will be sharing that file. All right, so if you look in the Zoom chat, I just uploaded a 32 kilobyte Game Boy ROM called Mission. I will also be throwing it in Discord. If you have issues downloading it, let me know. It shouldn't give you too much of an issue because it's very small. And then I'm also throwing up the Game Boy ROM in the Discord. You got a nice Windows message about it. Yeah, files with this extension may be harmful to your computer, but this one won't. And we will be looking at the assembly code so you can be sure that it won't. So don't be afraid of interacting with this Game Boy ROM. I have vetted it. It's okay. All right. So you don't need to have all the tools up in front of you, but if you want to, like I said before, we're going to be using Ghidra Boy with Ghidra and then BGB as the emulator. So if anyone needs the links to those, let me know, and then I can post those in the chat. All right, So I am going to start screen sharing. I have Ghidra up and running, and I've already done some preliminary reverse engineering of it. So I've kind of saved you all the pain of watching me fix some of the assembly instructions, because the auto analyze on Ghidra doesn't always work with Game Boys. So you have to go and manually hit disassemble for large sections of the ROM in order to get it to properly disassemble. So thankfully, you will not have to watch me do that. All right. So can you all see my Ghidra screen? I'm going to assume yes, because the chat is not pulling up right now. Okay, sweet. So I already loaded the mission Game Boy ROM into Ghidra, and I said auto analyze. I will actually just show you again what that looks like. So I am going to import a file, import that game again. Actually, I'm gonna switch my screen sharing so that way you guys can see all my Ghidra windows. So I think you're only just seeing one. Okay, so I'm importing this this Game Boy ROM, so mission.gb, and then I'm renaming it because I already have it disassembled and uploaded. When you upload it, if you don't have Ghidra Boy already incorporated into Ghidra, then you will probably see something different on this import results summary screen. I will be staying on after the meeting to help anyone configure Ghidra Boy if they want to get it configured. So don't fret if you can't follow along perfectly. I will be staying longer to help out. So you'll get a bunch of information, and you can see that some of the stuff we talked about is identified by Ghidra. So that address size, it's 16 bits. So we can see it here, that Ghidra was able to understand that, and then it understood that it's got like little endian, and then that CPU. The acronym isn't exact, but basically it's saying it's a sharp CPU. So then it talks about how many bytes the memory took up, and then we see that address range, and it corresponds to what we would expect a Game Boy ROM to occupy. So 0000 to FFFF. So this all looks great. It looks like it imported it correctly. It identified it as Game Boy, and we're good to go. So we can just hit OK. And then we can pull up that file. So double clicking will launch the code browser. And then we've got some analysis options. You can pretty much keep it as default, but I'm also going to hit decompiler parameter ID because it'll help, it'll like list parameters to functions in the decompiler window. So if it identifies parameters successfully, it will list those. So here's what I mean by you have to painstakingly manually tell Ghidra to disassemble. So you see all these question marks. That means it doesn't know what instruction it is there. So it already finished its auto analysis, but we have to go in and tell it to try again, basically. So we have to hit the D key, and then suddenly it'll understand, oh, these are all basically instructions we don't care about. And then there's an add, there's a load, jump, load, so on and so forth. But you have to keep doing that over and over again because there's more and more sections. So you have to keep hitting that D button, go down, and keep scrolling. So anytime you see this RST38, you can kind of just ignore it. Game Boy uses FF to indicate, like, instead of like clearing memory with zeros, it clears it with FFs. So you can just ignore all of those FFs because that means that memory is not, there's nothing there. Usually that's what that means. So you can just keep going through. I'm not going to subject you to all of that process. So I'm just going to show you the interesting stuff. So it takes a while to disassemble all of the interesting parts, as I say. So we know from our memory map in the slides that we talked about earlier that we only really care about the addresses like 0000 to 7FFF because that corresponds to the ROM section. And the reason why we only care about the ROM section is because that's the area that corresponds to instructions. So that's going to be the code, the logic of your program. It's going to be the logic of this Game Boy ROM. So if we need sprite data or if we need background data, if we need any IO stuff, we can go and access that later. But chances are what we need is actually going to be in the ROM. So I pretty much have it set up for static analysis, but I do want to show you what the game looks like. So that way we know what we're looking for. So I have BGB debugger up and ready for us. And then this is its basically its debugger screen. So you can see the individual instructions and then you can step through, you can set breakpoints, you can halt, you can reset, or you can just run. So I'm going to reload this ROM. So when you load the ROM, it will display a screen, but right now you don't see anything executing because I'm still in that debugger mode. So it's actually waiting for me to tell the debugger to advance before doing anything else. So if I double click in there, it starts executing. So we see that we have a mission that we have to complete. So our mission is to track down the rogue AI. Are you ready? So it's got this cool little intro. So it tells us that door needs a code, and then nothing else. So we know we need to find a code for a door. And then if we go to advance or do anything, those symbols pop up, and that's corresponding to my directional key presses. So when I press up, a little up triangle will appear. If I press right, a right triangle will appear. If I press down, a down triangle will appear. Left, left triangle, so on and so forth. And it looks like we've got a pattern going, and it says no good. So apparently the code for the door corresponds to some sequence of directional inputs. So we have to find a series of up, down, left, and right. We have to find that combo that will unlock the door. So we could spend a long time trying to brute force that, but that would take forever. It wouldn't be very effective, and we don't know which key presses are good. We only know once we submit all of them at the end. So we would have to get all 16 right, which is very hard to brute force that. And it would take forever. So we need to use our debugger and our disassembler, Ghidra, to basically figure out what that sequence is or find a way to bypass it. So we can go back to Ghidra. Now that we know what we're looking for a code, a series of inputs, and we can try and speed up this process. So we saw in BGB when we failed that check, it said no good, and it wants us to try again. And then it prompts us and we can put in a new input. So we should try looking for those strings that it's outputting, those words. So let's look for no good and see if we can find anything with that. So if you pull up your defined strings window, and the way you do that is you go to window and then define strings. And then it'll pull up on this right-hand side your defined strings. We see a lot of the words that we saw already. So like we already saw it say, my target is inside, I'm going in, you got it, boss, are you ready, so on and so forth. And then we see that no good message, and let me try something else. But we also see that worked, and first flag is. We never saw those when we were executing the program. That must be what happens when there's a correct sequence inputted. So we want to get to wherever this is being executed. So let's go look at first flag is. So first flag is stored at 2BD8. That's where those bytes are stored in memory. But we can also look at where it's cross-referenced. And so you can look at XREFs, which stand for cross-references for strings, and that will help narrow down what parts of the code you should be interested in, because we want to know where this is being spit out, what function actually prints that string, because that indicates a correct check. So I already went ahead and renamed the function. So originally this function was not called win. It was called like fun underscore 2b5d or something like that. But I renamed it to make it a little bit easier on you guys to keep track of everything I'm accessing. So we can go ahead and look at that cross-ref and then open the decompiler window on the right. So this is the win function. So we see that this win function calls a bunch of other functions. It grabs a value off the stack. It bitwise ORs it, does some other stuff, and then it prints, that worked, I'm in. And this is in well, this isn't in a while loop. It has some ending while loop, probably because Ghidra doesn't decompile it perfectly. So we can kind of ignore this at the end. So looking at this decompiler window, we don't get a lot of information. So we know that it's printing, that worked, I'm in, but we don't really know what else this win function really does. And so something that's helpful is looking at the function call tree of it. So you can look at the incoming references and the outgoing references. So you can see all the functions that win calls, and you can see those below, and you can see what function calls win. So we see that win is called by check. And once again, this is a function I renamed for convenience. So if we click check, we can see that it's setting some value to BA, some value to 3.8, some value to AE, so on and so forth. So we know that it's doing something there. But if we look down here, it says if local 3 is equal to hex 10, then call the win function. If not, call lose. So if we get here and 16 characters have been inputted, and the reason I'm making an assumption here. So I'm assuming that local 3 is corresponding to the length of the sequence, because I'm assuming because that character sequence was 16 characters, and then 16 in hex is 10. So I'm making an assumption there. So I'm assuming local 3 corresponds to the length of the sequence, because we also see that local 3 gets incremented here. So that's interesting. So either local 3 or local 2 is going to be keeping account of that sequence. But if we get there, we can either do, like, if we get through all of this, then we hit this. If local 3 is equal to that, then we call the win function. If not, we call the lose function. So we want to get here. We want to get to that win function. One of the first things you can try is patching. Patching is the easiest way to go. Or in this case, I'm not going to be patching the binary itself. I'm going to be changing values in the debugger during execution. But this is an easier way to go about it than to figure out the exact key presses, because I have less reverse engineering that I need to do if I just want to figure out how to patch it. So we need to make note of the win function, what address that's at, and then the check function, what address the check function's at. So the check function, we can see, starts at 2AA9. And then the win function starts at 2B26. So let's try something kind of quick and dirty, and let's try changing the program counter to the start of this win function. And the reason why I'm doing that is we may be able to actually skip all of the sequence checking logic and just have it print out the flag. That would be the best case scenario for us. But a lot of CTFs, you have to work a little bit harder than that, because they'll actually pull those values off the stack. But because they're doing it based on position, or key presses, sorry, there's a chance that they may not be stored in the stack. It may be, like, the flag may be displayed even if we don't have the right key presses. So I am going to reload this ROM. I'm sorry, you get to watch this intro again. So it's prompting us for the code. And then we want to jump to the win function. So that starts at 2B26. So we are going to set the program counter to 2B26. So it says enter new value for register PC, and we're going to enter that, 2B26. So now we are at the start of that win function, and we can verify by checking to see if 2B26 corresponds to the add df to the stack pointer, like the contents of df to the stack pointer. So let's go ahead and check that, and we get a similar instruction. So we've got add negative hex 12 to the stack pointer. So it's not exact. There may have been something that Ghidra did or the debugger did. So it looks close enough, especially if we look at the subsequent instructions. So the next ones are load instructions, and we can see the next ones are load instructions. And then an increase, and then let's see. Yeah, there's an increase HL. So we're definitely in the right spot. There may just be some differences with how Ghidra disassembles. So that's to be expected. So let's just go ahead and run it. Let's see if by changing the stack pointer to 2B26 and moving our execution to this point, we can just run it and it'll print out the flag. Let's see what happens. Oh, it's telling us that worked. So we successfully got into the win function because remember, it printed that worked and it prints something else. So yeah, it prints I'm in. All right. But we don't get the flag. We don't see first flag is like we expected. We see a bunch of zeros. So maybe things weren't as easy as we thought. Maybe it is pulling it off the stack and we can't just jump to the start of the win function and have it print out the flag for us. We need to succeed in that check. So the next thing we can do is we can go back and then go look at check again. So this is the check function. And then, so it sets some values here. And then it compares local 3 to hex 10. And then if so, print, go to the win function. If not, go to the lose function. So let's just try something quick and easy, see if it works. If it doesn't, we'll have to reevaluate and actually do some more reverse engineering here. So check starts at 2AA9. Let's see if we can just go to the start of check and see if it's actually just setting those character sequence values for us and pulling those from memory, like from the stack for printing the flag. So let's just go to 2AA9 and see if that works. So let's try 2AA9. So now we set our program counter to 2AA9, so that's the start of the check function. And now let's just run it to see what happens. All right, it says no good. Let me try something else. So apparently, just running the check function, because we didn't input anything, we're getting into that lose sequence. So I am going to just reset. Sorry. There we go. That's what I wanted. I wanted to reload the ROM. And you'll see this again. Yeah, very exciting. Oops. I'm just checking something to make sure. Yeah. So if we went to the start of the check function, yeah, we're gonna get that. We're gonna call the lose function. We're gonna fail. So let's try one last like quick and dirty thing. Let's try and jump to where that win function is called before we actually enter the win function. So it gets called 2B, 1B. So let's try just jumping there. And I inputted the character sequence like a random one just to like if it's storing the values, like the number of characters, like the number of directional inputs, that way it'll be set to 16, just in case it's checking. So we want to go to 2B, 1B, I believe. Let's double check. 2B, 1B. All right. All right, and then let's run. So it's saying that worked. I'm in. Oh, and here we get the first flag is, and then it prints the flag. So that actually worked that time. So we're done. We didn't have to figure out that character sequence. We didn't have to figure out the left, right, up, and down. We could just change the program execution to go to a certain part of the program and execute, and then it would just print out the flag. So that's really interesting. That shows us the power of static analysis combined with dynamic analysis. There's almost always an easy way to do CTF problems. So like, especially for reverse engineering, there's usually an easy way and there's a hard way. And I am all for taking the path of least resistance, going for the easy, lazy solve. So that's what this was the easy, lazy route. Just changing the program execution versus reverse engineering the button presses and finding out what sequence you needed. So you guys basically solved your first Game Boy reverse engineering challenge. So this was from Square CTF 2017. I'm not sure how many points it was worth, but you guys now all have the skills to solve that challenge. And if you would have done Square CTF, you would have gotten that challenge. You would have gotten however many points it was worth. And so now you should feel confident in being able to look at a Game Boy ROM, load it into Ghidra with Ghidra Boy, narrow in on points of interest, and then using those points of interest kind of move back using cross-references, and then based on the cross-references, finding out where your win and where your lose functions are, and then manipulating the control flow using a debugger to get to that win function and allow the program to set everything up for you so that way when you get to the win function, everything is like everything on the stack is in the right state. You're not corrupting anything. So that was kind of a quick and dirty Game Boy CTF challenge. I'm going to check the chat real quick to see if anyone had any questions on that, because I went through that kind of fast. So if I didn't have a way to run the Game Boy files, would you be able to statically analyze the win function? I know it wouldn't be optimal because it only relies on the size of your input. Yes, you'd be able to statically analyze the win and check functions to see what that expected input would be. That's one way you could solve it. It takes more work because you have to understand how the key presses are being stored in memory, and then you have to basically compare each key press to what the expected state is in check, and then based on that you have to compose your sequence. So you can definitely do it purely statically, but you would most likely still have to run the program in order for it to output that flag, because it's not like XORing those key presses with a sequence to get the flag. I think I believe it's just doing a check on the key presses, seeing if those key presses correspond to what they should be, and then it's doing some XOR from somewhere else and some like shifting, and then it's printing the flag. So you could potentially do it purely statically, but it's harder to know if you're on the right path, and it would take more work. It's definitely much easier to do a combination of static and dynamic analysis for most Game Boy challenges. Did that answer your question, Owen? Okay, sweet. Does anyone else have any questions on that challenge? Yeah, the flag isn't in plain text anywhere. It has to be retrieved by actually looking at the individual key presses and then making sure that they pass the checks, or looking at when first flag is retrieves from memory. We saw that when we didn't have the key presses in, it printed out all zeros. So that shows that if the key presses aren't inputted, then whatever transformation is happening on the key presses won't occur, and then we won't be able to print out the flag because the flag will just be all zeros. So you could definitely reverse engineer it statically, but it would be more work, and you would need to understand that initial, like how the key presses correspond to the flag bytes. Let's see. Does anyone need any help getting set up with BGB or GameBoy? Oh, also, I was going to show you VGBA and Visual Boy Advance. So let me do that real quick. So you guys saw BGB here. So I'm going to close out of it. And then I'm going to pull up Visual Boy Advance. So Visual Boy Advance is pretty similar. So you can, sorry, I need to open GB. So it has, its default open is for Game Boy Advance. But if you want to load Game Boy cartridges, like Game Boy ROMs or Game Boy Color ROMs, you choose the corresponding option. And then we can see, we can keep going through that. You guys recognize all the same stuff. I'm not going to make you watch this sequence again, but I will load actually another challenge. And so I already modified the settings to make this work. But you do have to change the settings a little bit if you're going to do Game Boy games. So you would go to Options, Game Boy, and then Configure. And
Hey,
then
Claire.
switch this to automatic. Before, like, the default is Game Boy Advance. So when you first download Visual Boy Advance, it'll be set to Game Boy Advance. Go ahead and set that to automatic, and it'll identify whether you're loading a Game Boy Color or Game Boy Advance ROM. And then
Can you hear us?
And then
Nope.
Hello, Claire. Can you hear us?
wait, sorry. Let me raise my volume. Okay, can you repeat yourself? Sorry. Oh, my screen sharing was paused. All right, how long was my screen sharing paused?
The whole time?
When you mean the whole time, how long?
Oh, when you started explaining the new stuff,
Just
like
Visual Boy?
disassembly. Yeah, Visual Boy. Yeah.
Okay, sweet.
Disassembly.
I got worried there when you said the whole time, and I thought you meant like the entire previous CTF challenge.
No.
Okay. So this is Visual Boy Advance. So you have by default open, and that expects a Game Boy Advance ROM, open GB, so that's your original GB, your original Game Boy ROMs, and then open Game Boy Color, so your Game Boy Color ROMs. So we were working with just Game Boy. So let's load Mission Game Boy. So you recognize that same sequence. By default, though, you have to change the options for Game Boy. Go to Configure, so Tools, Options, Game Boy, then Game Boy Configure, and then change this emulated system to automatic. So I already changed it, but if you had it set to Game Boy Advance, this is the default. By default, it's set to Game Boy Advance. And then you went to open this. It will get a little funky. So it's trying to play it like a Game Boy Color game. So you see like the colors are wonky. They're not black and white. It's not grayscale. That's because it's trying to play it as a Game Boy Color game, which usually you're okay with that, but it can lead to some really wonky stuff. So I was trying to do a game earlier and the inputs weren't working. So yeah, we see it again. I'm doing key presses on like doing up, down, left, right, and we're not seeing the symbols appear. It's not logging them. And that's because you need to go to Options, Game Boy, Configure, Emulated System, Automatic. So that way it automatically identifies which ROM you're working with, like what type of ROM. And then if we, once again, load, sorry, this time it'll work. But yeah, you got to see this. Yeah, See, now the inputs work just fine. So that's Visual Boy Advance. It has some cool tools. So it has a disassembler like BGB. So you can go through and you can see the flags here. You can see the values of the registers here. And then you can say go to PC. So in case you are looking elsewhere, clicking go to PC will just bring you back to the current instruction. So, and you can tell it to advance instructions by clicking next. You can also look at memory. So you can look for specific values in memory. So this is just the whole memory space, 0000 to FFFF, and it crashed. So that's one of the problems with using these emulators is they are prone to crashing a lot because they're user made. They are usually only maintained by one person. So I find Visual Boy Advance crashes a lot for my uses. BGB is much more stable. Then, sorry, you're gonna see all my files. Then MGBA, I will show you that. Another feature of Visual Boy Advance that's really cool is it supports cheats. So you can basically create sequences of actions, like sequences of instructions, and have those execute as cheats. And then you can save them and you can create cheat tables. And that's pretty cool. So now looking at MGBA, let's load a ROM. So we'll load Michigan, and it automatically scales that, which is awesome. So it can extrapolate what that 160 by 144 pixel display would look like if you expanded it. So it scaled it up, which is really nice, so you don't have to look at a tiny, tiny screen. So yeah, it's in grayscale, so you can tell it loaded properly as a Game Boy original ROM, not a Game Boy Color or Game Boy Advance. And then, yeah, we can do our key presses and so on and so forth. This also has cheats, like cheat support. Yeah, here. So you can add different cheats, add different codes, and then create cheat tables. Then you can open a debugger. So it doesn't by default display all the instructions, so you have to tell it to do so. So disassemble. So you have to tell it to disassemble. So it only by default disassembles the first instruction. If you do, okay, never mind. I'm sure you can get it to disassemble more than one instruction, but I am not familiar with its syntax. If you do dis10, it disassembles the instruction at hex A. Maybe you can do, no, you cannot do it that way. Okay. I don't use MGBA a lot because I don't like its debugger. I think it's annoying. So that's my personal preference, but it gives you all the same functionality. You can disassemble, you can set breakpoints, you can continue execution, you can list what's at, you can like print the memory at a certain location. You can set watch points, which is really nice. So you can basically tell the debugger to watch for when there's a read or a write to a certain memory location. That's really helpful. That's one cool feature. And then BGB, Visual Boy Advance, and MGBA all have the ability to view palettes. You can view sprites. So we can see the back of our person's ponytail there. And we can see the tile, the 8x8 tile that corresponds to it, and then the palette number that corresponds to it. So this is sprite 1, so that's the back of the ponytail. Sprite 0 is the back of the ponytail. Sprite 1 is her face, and so on and so forth. So this is helpful for understanding sprite memory, and it also tells you where in that OAM memory that sprite is located. So 8010. So you could then go into the memory view and you could look at the values at 8010 and you could see it corresponds. Then you can view tiles. So all of the tiles that make up the background, you can see them all laid out. So, sorry, I'm going to check the chat real quick. Okay. I will pull up the debugger and try disall. No, that didn't work, but yeah, I'm not super familiar with its debugger. Sorry, I realized I paused my screen share, but I just tried running disall in the debugger and it gave me an error. So it can be finicky. And then if you do view map, this is the background. This is your background 1 map that you're looking at. And you can also look at windows. So we see that window no good. That's the no good is a window. It's another layer on top of the background. So when I was explaining the difference between background, window, and sprite, maybe this makes it a little bit more clear how those different things interact. So the girl is a sprite. Everything here is the background, and then the no good is a window. And you can see what tiles correspond to which part of the background. You can see where those tiles are located in memory. And then you can see the colors. You can view memory, same kind of memory layout as before. You can search in memory. And then I forget which one it is. Oh yeah, you can do fast forward speed, so you can have it go extra fast. If it will respond. All right, it's currently not responding, but you can set the fast forward speed so it runs at a faster rate. You can also rewind, you can step backwards. You can do some fun things with external peripherals like the GameBoy printer. So each one of those Game Boy emulators and debuggers has certain strengths and certain weaknesses. I personally like BGB, but that's once again a personal preference. You may find that you like a different debugger. So that kind of concludes what I had because we're running over for time. But I will be staying afterwards to help anyone set up if they need to set up GameBoy or BGB or another emulator. So thank you so much for coming out and for giving me your time. If you have any questions about anything I talked about today, feel free to unmute yourself or type in the chat. I'm sure I misspoke at least once during this presentation, so once I go back and review the presentation, I will post any corrections that I may need, um, and I'll make sure that the slides are pristine. I don't think there's any issues with the slides, but I think there may have been times where I misspoke. So I will make sure to have that ironed out for you once I post the slides and post the recording. And I'll be posting the recording will go on YouTube, and then I'll be posting it in Discord. All right. Thank you again. This is going to be the end of it. So feel free to take off, or if you want extra help or want to ask questions, you can stick around. I wasn't planning on going through another CTF challenge, but if people really want, I can do that too. All right. Thank you so much for attending, everyone. Have a great night.